Double checking now. Or is it the screen? Yeah? Display capture was a little faulty. Alright. Let's just reiterate. So you can hear me? Yep. Can you see the screen? That's the one thing we have to double check. Alright. That was a shame. Let's get back into that, alright? So, Thevenin B, attendance sheet, moving into the OneNote. So, we have our Thevenin methods for our stuff, and we're going to be running through these questions, alright? Let's do it. So, 3 methods as described by your lecture slides. Method 1, I've identified probably the necessity of these methods, okay? You cannot use methods 1 and 2 if you only have dependent sources, and so we have to move on to number 3. Although, you can actually use number 3 in all scenarios, right? Mind you, we add an asterisk here just to say that you have to also turn off the independent sources. To use it. Alright, so let's get into it. Let's begin with question 1. We have a rather simple circuit. The way we run through these ones is there's actually a number of ways you could actually purely do this via source transform, which would be pretty cool, but let's just think about how all 3 of these methods work for this one. Method 1, if we attempt to find Thevenin, we just say Thevenin equals VAB equals I, which is 7. So I'm actually just going to write 7 times R1 parallel R2. Right? Regardless of their values, we'll do that, and we'll get Thevenin. Now we calculate Thevenin. Method 1, we just turn off the source, becomes an open circuit. So let's illustrate that. Just becomes an open circuit, so this would get crossed out in that method, and we equate equivalent resistance, which will just be R1 parallel R2. That's method 1, okay? Method 2, we would calculate the I short circuit. So we would go ahead and draw in a line at our output, well, between our terminals that we're measuring our Thevenin equivalents, and determine the current going through this. Now, because this is a short circuit between our 2 nodes, it's going to be all the current, right? And it'll just be 7. Please enter. And if I divide Thevenin by this value, I end up with, quite frankly, R1 parallel R2. So that's methods 1 and 2 verified. We can verify method 3, and it's a rather funny way. We go ahead and we turn this off, so that becomes an open circuit. And at the terminals, we can plug in a 1 amp supply, right? And now we just need to find VAB. And quite frankly, we know this can be equated as 1 equivalent resistor, R1 parallel R2, and we know the current coming out of it. If we know the current coming out of it, we know the voltage. Yeah? Fantastic stuff. It may be a little bit more intuitive for me to go like this, and then I can say, okay, current's going that way, therefore I get a positive, negative voltage there, right? And so that is how we work those out. Fantastic stuff. And they all give us the exact same answer of R1 parallel R2, right? Fantastic stuff. We'll move on to question 2 now. Let's go at this. The questions will steadily increase in difficulty until maybe question 10, and then they'll be a little bit miscellaneous, all right? So let's do this. Question 2. It is also another similar circuit. You could apply a source transform 3 or so times here, but what we're going to do is just throw our head at it. Okay, so Thevenin, easiest way in my opinion to find this is you go and just calculate currents through. Okay? You could do a current divider right here, followed by a voltage divider to find VA. Since in a lot of these scenarios, VB is just, we're going to take that as 0, right? So these are the things we can do. So, Thevenin, let's first find VA and VB. Sorry. Let's find Vx, then VA, right? So Vx, we can calculate equivalent resistance right here, which will be 100 parallel to 75. Sorry, 100 plus 75 parallel to 30. Okay? So that's our equivalent resistance right here, and we know how much current is going through that. The current going through that is going to be 50 amps, so times 50. This much is going to be equal to Vx. Alright? We know that VA is just a voltage division of Vx. So we say VA equals Vx times the voltage divider. We're finding voltage of this one, this 75. So we put the 75 up the top over 100 plus 75. And so Thevenin, I'm going to put these in exact values without simplifying them at all. That's left as an exercise to you. Just because, quite frankly, I don't have my calculator with me. Alright? And it's all about methods. So, let's do this. Thevenin is going to be equal to VA, which is equal to Vx, 75 on 100 plus 75. It's a plus. Which is going to be equal to big numerator of 175 parallel 30 times 50 times 75 over 175. Right? Fantastic stuff. So just going to highlight that as Thevenin. Then for Thevenin, we can just turn off the source and find the equivalence. Now, mind you, the equivalence actually swaps sides right now. Before, we were calculating this stream and this stream as being parallel. But when we turn off the source and cross it out, it opens circuits because it's current, and the parallel lines actually come around this way. So, let's go ahead and work that out. I'm going to keep that as VA. And so, our Thevenin is going to be equal to 75 parallel 130. Bam. This is method 1. Okay? Method 1, up here, we can use method 1 as well. We're going to move on to question 3. A lot of these are just going to be method 1, just so we get a fair bit of practice. Question? Pardon? Yes, it is. So, let's actually let's think about this. Either you can copy questions off this immediately or the Discord. Yeah. Alright. At the end of the video, I might just put up a QR code of the Discord server. So you can enter the Discord, get verified with UNSW, and then have free access of this, which is on our drive. All right. You can also locate it via our website, so that is also something cool. All right. Nice stuff. Let's move on to number 3. What's going time-wise? Fantastic. All right. 3. Thevenin now. How do we calculate it? Please do not say 4 source transforms. That would be rather silly, but it would work. So instead, we just get some manner of voltage dividers. Now, just remember, we're not dividing this bunch right here. We're not doing that because there's obviously this amount on the right-hand side that is parallel to the 100 ohms. So we actually have to find the equivalent resistance here to actually voltage divide. Okay? So let's make sure we do that. So, once again, Vx over here, Va over here. Vx is going to be equal to the voltage division of this equivalence on the right-hand side between Vx and Va. So we say the voltage amount we're looking at is 100 parallel to 150 plus 100, which would be 250, divided by 50 plus the same thing. Right? And then, so that's a voltage division. Vn is just going to be 3. Okay? And so we have this is all set up. Fantastic stuff. And now we can calculate Va. Va equals Thevenin, which is going to be equal to the voltage division once again. So we go 100 over 250, because 100 is what we're looking at. That's the voltage we want. The total is over the 250, and the same current is going through them. A common mistake with these questions is to think about, oh, what about the current going into A? Let's consider this. It is an open circuit. That's why we're actually calculating equivalence over terminals, and therefore there is no current going into here, right? And so we're allowed to consider voltage division as such. It's all the same node. Don't think too hard about it, right? So 100 over 250 is the voltage division. Now we need to include Vx, and Vx is going to be 100 parallel 250 over 50 plus 100 parallel 250. All right? Fantastic stuff. Now to find R Thevenin, we can again use method 1. I'm going to keep on saying it, so I'm just going to put 1 over here. And we can actually do this somewhat similarly. So look at it from the terminals of AB. AB will give you first 100, and then we're going to have a big rest of it. So the rest of this stuff is going to be parallel to the 100. So we begin with 100 parallel to everything else. We'll begin with a 150, but then it branches up into 2 parallel lines. Mind you, we are short-circuiting this because it is a voltage source. That is how we turn it off. So now the 50 is parallel to the 100. Okay? And bam! That is our Thevenin. Enter. Yeah, take a seat. This is the solution session. Questions are on the Discord and website. All right. That's good. It's a bit different this time. Yeah.
So I'm
Sure. All right. So, question 4. Thevenin. Let's think about this. This is a bit of a convoluted circuit. Hasn't particularly copy-pasted the best. So let's just draw in the lines that we can see. Let's not jumble up everything. The lines go as such. Like that. Now, we have a dependent source this time. So this guy is looking like a diamond, and the rating of the diamond is going to be 0.001 multiple of V plus minus V minus, right? So that's how we're going to think of this thing, okay? Now, really a goofy thing with this question is there's this division between our two things. We have to ask ourselves, can any current actually go through this and interact with the rest of the circuit? And the answer to that is actually no. Because to have current going out of a circuit, you need current going in. That's our meshes, that's our KCL, right? And so, rather KVL, KCL, it's both. It's just a conservation of your charges, right? So you have this mesh, you have that mesh. There's no external mesh, right? You only have these three meshes to think about. And now when we're talking about terminals A and B, there's only really one thing to consider. So it's a bit of a trick question, yeah? So let's think about this. To the terminals AB, we have a voltage source with a minus 4,000 volts. And let's think about how this goes. Let's voltage divide to find VA. So V Thevenin equals VA, which is going to be equal to voltage division across these values. So you get 3.6 K on the total, so 2.3 K plus 3.6 K multiplied by minus 4,000, right? Multiplied by minus 4,000, not just subtract 4,000, right? Okay, so that's V Thevenin. Now to calculate R Thevenin, again, method 1. And so, using R Thevenin, method 1, this short circuits, and we just get 2.3K parallel to 3.6K, right? Now we have some slightly more interesting circuits. A lot of this will be, again, method 1 to calculate R Thevenin. So the real tricky bit here is calculating V Thevenin, right? And so, let's think about our nodal and mesh analysis. So, question 5, V Thevenin, I will not bother calculate. Actually, depending on time, we will potentially skip V Thevenin or R Thevenin in future, but we'll see how that goes, okay? We'll see how far we go. Question 5, V Thevenin. Let's think about this. So, I like to use mesh here, just because I see two loops. Alternatively, you could use nodal. It is the exact same in terms of measurements and such, because nodal, this is one supernode, because we already know the voltage right here. So you just use this point right here as your node. You wouldn't need to consider this one. And you'd use this node here. For mesh, we already know the mesh current here, and so we only need to consider the mesh current over here, right? Because this is not a mesh, right? It does not close. It is an opening of the terminals, right? So let's do this. We apply a mesh, and it tells us immediately how much current is going through this 50 ohms. So V 50 ohm is actually going to be equal to, mind you, this is minus 2 volts, sorry, minus 2 amps running into here and going around into the mesh. So you actually have 2 volts going that way. We think about voltage drops, and therefore this node over here we can calculate the voltage of, right? So V50, and that's going to be minus VA, is going to equal to 50 times minus 2, right? Because minus 2 is our current. So let's keep on doing this. This calculates that voltage. Now we need to know the voltage relative to ground. So V50 ohm, I shouldn't call that V50 ohm. I should call that Vx. Yeah, because this here would be V50 ohm. Yes. All right. So that's Vx in relation to VA. Now we need to do it in relation to ground. We're using another mesh here. We just do our mesh analysis. So we say minus 20. We're going around the mesh this way. So minus 20 plus 1K times the current there, I2, plus 2K times I2 equals 0. And this 2k times I2 is going to be equal to Vx. Alright? So we can calculate for I2. So I2 is going to be equal to 20 on 3k. Right? All happy with that? Fantastic stuff. And so Vx equals 2k times this. So it's 2k times 20 on 3k. The thousands cancel out. Equals 40 on 3. Alright? And so VA equals V Thevenin equals this bit, the negative of that, because I'm bringing it over to the other side and swapping it over. So it's going to be Vx minus 50 times minus 2. Okay? So equals Vx minus 50 times minus 2. Alright? So in other words, it's just going to be 100 more than Vx. Yeah? So it'll be 100 plus 40 on 3. Good stuff. Alright. Very happy with that. And we can calculate our Thevenin now, the truly tricky bit. Or maybe not. Alright. Our Thevenin, once again, as we mentioned earlier, method 1. Actually, yes, method 1. We are only using dependent sources over here. Sorry, independent sources over here, losing my mind. That one crosses out, that one short circuits. We get 50 plus the parallel of 1k and 2k. So let's write that down. Fantastic stuff. Alright, let's keep on moving. Question 6. Alright, question 6. Let's think about this one. We have a bunch of independent sources. I wonder which method we're going to be using to calculate our Thevenin. I know this is getting a little repetitious, but let's keep on pumping forwards. So, how do we do this? I see a few nodes. I also see a couple meshes. You can do either method. I like nodal here, just because it's one big equation. I kind of just lied and said it was 2 nodes. It's 1 node. So, VA, nodal. So we say VA minus this voltage over here. So VA minus 3 on 50 gives me the current going out of this. Remember, nodal, I'm just calculating currents out equals currents in. So currents out, I have this, VA minus 7 on 77 plus VA minus 11 on 23. And that equals the currents coming in, which is 0 so far. I like this method of saying, oh, I'm going to assume everything to going out, and then say, okay, so then VA minus surrounding voltages over their respective resistances is equal to 0. Because this allows me to group up VA very easily, very quickly. And if something is in actuality, because quite frankly, maybe one of these is actually going into the circuit, just looking at that sneaky VA minus 11, if one of them is going in, it's actually just going to give me a negative sign on its own if I assume it going out, right? So I don't need to worry about that too much. Just assume it'll fix itself, right? Take a valid assumption, stick to that, be consistent, and you'll be happy. So I'm going to use this method, group VA. So I got 1 on 50 of that, plus 1 on 77 of that, plus 1 on 23 of that. So that's me just crossing out these terms over here. And I'm just going to throw the other ones over here, right? So this is going to be equal to 3 on 50 plus 7 on 77 plus 11 on 23. And we're going to do a little trick called use the iPad and just move that onto the denominator. Okay? Bam. We have an answer. Yeah? Let's neaten up a little bit. Maybe a little better. Wow, it really doesn't like to select immediately. Maybe it's because I've got too many things running. Anyways, that's VA, that's Thevenin, right? So we can be really smart about our algebraic catch, right? Playing a game of catch without algebra. We throw everything we need all together on one side to begin with, and it really speeds up the process. So let's keep on moving. Fantastic stuff. Thevenin. Now our Thevenin. Once again, do you want to take a guess at which method we're going to use here? I only see independent sources, and therefore I'm going to use method 1. Alright? They're all voltage sources, so they do all short circuit, and I'm left with a big parallel. Yeah? So 50, parallel 77, parallel 23. Fantastic stuff. Now, we have question 7 here, which I'm going to invite our trusty academics director, Laith Alani, to help us solve. This is a special question concerning max power transfer. All yours.
Thanks, Otto. Hey guys, so I'll be just taking question 7 and I'll be doing the solutions for question 7, yeah. And this question is slightly different to the other questions that we've already covered. You'll still be using method 1, which we'll see soon enough, but as you can see at the bottom here, for RL, we've already included a variable load resistor, and so that's sort of like there to test if you guys know your maximum power transfer theorems. It's fairly straightforward though, so it shouldn't be too much difficulty. So for this problem, the thought process is fairly similar to what we've done before. As you can see, we've got 2 independent sources and we don't have any dependent sources, and so as a result it's prime for the first method. What we can do is that we can easily apply we can easily find RTH, or the Thevenin resistance, so we might as well find that first. So in order to find the Thevenin resistance, we have to turn off all the independent sources. So that would mean we would turn off this and we would turn off this, and as a result both of these sources would become short circuits. Now if we label all the nodes in this circuit diagram, we can see that this right here is one node, this is another node, this right here is another node, and that's another node. As a result, as you can see, from terminal A and terminal B, if we of course ignore the load resistor, we can see that all of these 3 resistors right here, the 5 ohm, the 60 ohm, and the 45 ohm, are all in parallel. And so as a result, we can easily find RTH by just taking all of these resistors in parallel, simplifying it, and that becomes our RTH. So we can say that we are to find RTH, we can do 5 parallel 60 parallel 45, and that will be the resistance as seen from AB. So that would be equal to RAB, which is also R Thevenin. Oh, that's wonky looking R. And this actually comes out to be equal to 4.186 ohms, if you just want to check your answers. Now, for the second part, we have to find the VTH. So, in order to do this, it's fairly simple. We've already labeled our nodes here, so it would probably be pretty easy to apply nodal analysis. You can probably use mesh analysis. There is another way to solve this using source transformations, which is a bit of a trick, but for the purposes of this question, just to keep it sort of consistent with your thought process during the midterm, we'll just use nodal analysis. So what we can do is that we can just start labeling these nodes. So we can say that this is V1, we can say that this is V2, and we say this node down here is V3. Now, after we've labeled these nodes, we can start trying to extract information from this circuit, what we can see is that if we treat this down here as ground, so this is 0 volts, this is the same as B, so B is equal to 0 volts right here. And so what you can see is that V2 will just be 15 volts because it's just above voltage sources. So we can actually get rid of these. That was from the Thevenin resistance. So we can say that V2, if finding VTH, we can say that V2 is simply 15 volts. So that was very easy to get. The other two are not as easy to get. So what we can see is that if we wanted to do KCL at 3, we can't because we have the voltage source right next to it. And so what we can do is that we can form a supernode using voltages, using the V1 voltage and the V3 voltage. So we can see that if we're subtracting V3 from V1, then we can get it. We can get the voltage across them to be 20 volts as per the voltage source. So that would be V1 minus V3 is equal to 20. So that's equation 2. We can label this 1, label that 2. Now, equation 3 is a bit harder to get. So what we can do is that we can apply KCL from node 1, or node so V1. So what we can do is that if we apply KCL there, then we can see that if we label our currents like this, it's a bit arbitrary, but it will just help with the calculation. So these are our currents. We can say that at V1, we can say that V2 minus V1 over 5 is equal to, so that's the current going into V1, and we can say that that is equal to, sorry about that, you can see that. So that would be the current that's going in to V1, and so that would be equal to the current flowing out. And we don't know the current that's going down, straight down from V1, but we can say that that's equal to the current that's going through V3 because it's through the same branch. So we can say that V3 over 45, so that's V3 minus 0 because it's just next to ground, so the V3 minus 0 over 45. And we can also add the other current going out, and that would be the one diagonal. So that would be V1 minus 0 on 60. Now if we clean this up a bit, if we just move all the voltages into one side and then make it into a sort of like linear form, we can say that this equation simplifies to this, so it would be 1 on 5 V2 plus 1 on 45 V3 is equal to 0. And this is equation 3. Now, using this equation, and this equation, all three of these equations, we can solve them simultaneously in order to find V1, V2, and V3. You can use multiple different ways to solve them. You can use a matrix and then solve using Gaussian elimination. You can just sort of substitute one into the other. I can just quickly give you the answers for them. So V1 would be equal to 620 on 43 volts. V2 would be equal to 15. That's very apparent because we already found it earlier. And then V3 would be equal to negative 240 on 43 volts. 43 volts. Now, we found earlier is that we want to find VTH. And VTH would be the voltage across A and B. Now what we can see is that because B is 0 volts, the voltage A would be just the voltage right here, which is the same as V1. So we can just say that VTH is equal to V1, and that's equal to that 620 over 43, which is just 14.42. So that's the first part of this question, which is finding RTH and VTH. Now, the next part of the question is that we need to find the max power. Now, this is actually very easy. For the purposes of your midterm, you're better off just like memorizing these formulas, but you should also understand how to derive them. So in order to find the max power, if we accept that this resistor, this load resistor, actually exists in the circuit, we can find that in order to maximize the power absorbed by that resistor, RL should equal to RTH. So RL should equal RTH, which is equal to what we found earlier, which was 4.186 ohms. And then we can find the power that runs through that element at that resistance simply by just doing VTH squared on 4 RTH. And if I just plug that in, we should get something close to 12.4. Oh, that's a weird looking 12. Let me just clean that up. .42 watts absorbed by the resistor. And that is question 7. Fairly simple. Just method 1 and just a bit at the end with maximum power transfer. But yeah. We'll skip over 8 real quickly, and then we'll just do question 9 and then question 10, and then I'll hand it back over to Aldo. So, for question 9 is quite a bit different. It's also a good bit harder. It's probably one of the harder sort of questions you would look at during your midterm. So for this question, what you can see is that we don't actually have any independent sources. What we have is that we have 2 dependent sources. So we've got this one right here, we've got this one right there. As a result, what we can say is that because both of these sources are dependent and there's no independent sources, all the voltages and all the currents running through this circuit as is with no other source applied is 0. So this would be like a 0 current because there's no power going through it. This would be 0. All of it would be 0. We call this a dead network. And so as a result, VTH is very easy to derive. You can just say that VTH is equal to 0 volts because we have no power running through the circuit. And we can just say that is because of a dead network. Now RTH is a lot harder to find, so finding RTH. Now if we go back to the 3 methods that Otto outlined earlier during this live stream, we can't use method 1 because we don't have any independent sources. We can't actually use method 2 either because we don't have at least one independent source because everything here is dependent. So what we have to use is method 3, which is we have to connect a power source to the terminals of A. So if we can assume that this is a source that's connected to these terminals, then what we can do is that let's just say that this is a current source, for instance. What we have to do is that we have to find the voltage across this current source. So we have to find voltage of, let's say V, we'll call it VC. C for current source. Now you could also attach a voltage source, and it doesn't actually have to have a value of 1. You can have like 5 volts, you can have like 20 amps, but we're just using 1 amp right here just for simplicity's sake. Now, in order to solve this, there's also multiple different ways you can. You can, of course, use nodal, you can use mesh. Mesh might be a bit easier here, but we might just use nodal because I find that a lot of students are uncomfortable with nodal, so we might as well get some more practice with nodal. So we label our nodes for this question. We've got V1 at the top here. We've got, let's just call this down here V2, and we call this V3. So these are our 3 nodes, and we can apply nodal pretty easily. So what we can see first is that very obviously that we do have a supernode. We can see that between V3 and V1 there's a voltage source. It's a dependent voltage source, but it is a voltage source. And so if we subtract V3 from V1, so we do V1 minus V3, we can say that's equal to 2VO, and that's because supernode. Next, we can do KCL at V1. So at V1, we can say that the current going through, wait, hold on 1 second. Oh, I mislabeled. That's fine. Just say that we'll do KCL at V3. KCL at V3. So what we can say, oh wait, no, sorry, it is V1. My bad. So at V1, whoop, that's very ugly. We can say that we have 3I, 0, going into the node, and we can say that we also have the 1 current going through this through this current source, and then we can equate that to I0 coming out, and that's equal to V1 minus V2 on 10, and 10 is for the resistor. And then at V2, so if we do KCL at V2, we can say that we have the current going in, V1 minus V2 over 10, and that'll be equal to V2 on 35. Oh, that's a bad looking 35. Now, given these equations, we can also derive from the circuit, we can try to find what VO and IO are in terms of V1 and V3 and V2. So what we can see is that VO, which is right here, is exactly the same as V2. So we can say that we know that VO is equal to V2. And we also know that IO, which is coming right through there, is equal to V3 minus V2 on 25. So IO is equal to V3 minus V2 on 25. Now we substitute all of these in, so we substitute these 2 values into this one, into this, and into that, and also into this. We can get 3 equations. So for one, I've just simplified it a bit, so we can do V1 minus V2, V2 minus V3 is equal to 0. Our second equation that comes from V1, KCL at V1 that is 1 on 10 V1 minus 1 on 50 V2 minus 2 on 25 V3. And that's equal to 1. And then our third equation becomes, let me just scroll down a bit, 1 on 10 V1 minus 59 on 350 V2 plus 1 on 25 V3. And that's equal to 0. Now, from these three equations, it's a bit like what we did earlier. We just have to solve them simultaneously. And so there's different ways you can do it. But once you've solved these, you can get the three values for V1, V2, and V3. And those are V1 is equal to 435 on 43. V2 is equal to 245 on 43. And V3 is equal to minus 55 on 43. Now, we don't actually care about all of these voltages. We just need one. And if we look back at the circuit, what are we trying to find? We're trying to find the voltage VC. And VC is just the voltage across A and B. If we say that this is ground, then what we do know is that VC, which is just VAB, is equal to V1. So we go back down. We can say that VC is equal to VAB, which is equal to V1, which is equal to 435 on 45. Then, using Ohm's law, we can take the ratio of the voltage across VC with the current going through it. So current going through that current source just over here. So we can say that RTH is equal to VAB on 1 amp, which is equal to V1 on 1 amp. So if we just substitute that value in, we just get, well, I'll just put it in decimal form, 1.12 ohms. So that's how we get RTH, which is right there. And then earlier we got VTH very easily, which was just 0 volts. And yeah, that's question 9. Question 10, so if I do question 10, question 10 is a bit similar. It's actually quite similar. It's the same sort of method, so we can see here that we don't have any independent sources. We only have the dependent source, which is the voltage source right here, the 5 VI. And so as a result, we have to use method 3. You can also see that this is a dead network. So as we already know, the voltages in the circuit without an external power supply would be 0. So we know that VTH is simply 0 volts. Easy. Now for RTH, RTH is a bit more complex, but it's actually a bit easier than the previous example. So what we can say, let me clean that up, is that let's analyze this circuit. So I guess in this instance, let's just use nodal again, just because we've gotten quite comfortable with it. We can say that this right here is V1. V1. Over here we'll call this V2. Over here we'll call this V3. And we have to connect a source here in order to analyze. And so we'll just use another current source. Now, if we analyze this using nodal analysis, what we can see is that V1, if we say that right down here, never mind. It's not what I wanted to do. This is 0 volts. So we can say that V1 is equal to 5 IO, just because it's connected to the other terminal from this current source, or from this voltage source, that is, sorry. So we can say that V1 is equal to 5 IO, and actually we can find IO pretty easily, because IO would just be across V2. Ooh, these annotations have been moved a bit. Oh well, that's frustrating. Let me just fix these up. So that's supposed to be V1. That's V2. And that's V3. And this is obviously a current source. That's 1 amp. Yep, so we can say that IO is just going to be V2 minus ground, so that's 0 on 16. So this is going to be equal to 5, so that's going to be V2 on 16. Oh, and that's our equation 1. That's fairly easy. We can also do KCL on V2. So if we look at V2 over here, we can say that we have V1 minus V2 on 22, which is the resistance, plus the current from that source. So we see that current is coming into the that node. So this current, we can define this as that, define that as that. It's equal to 1. And that's going to be equal to V2 on 16, which is just the current going out. And this is equation 2. And then from V3, we can do another KCL. So we can say that we're looking at the current going down here, current going out of this node, and the current going down here. So we've only got one current going in, so that's going to be V1 minus V3 on 8, and that's equal to the one current going out plus V3 on 30, and that's our equation 3. And so as a result, we've got these 3 equations, and so we can solve them fairly easily. Just have to rearrange them a bit, and then you have to substitute one into the other. I would probably substitute 1 into 2 and 3, and so as a result we can eliminate our V1s, and so you just have 2 equations with 2 variables using V2 and V3. But if you do solve this with whatever method you choose to use, you'd find that V1 is equal to 10 on 3. We'd find that V2 is equal to 32 on 3, and we find that V3 is equal to negative 70 on 19. Now we want to find the voltage across AB, which is our Thevenin. Now the voltage across, so that voltage across is going to be V2 minus V3, which is what we found earlier. And that's going to be 14.35 in decimal form. Now we've got our voltage across that source, voltage here, so we'll just call that VAB. In the same way, we can use Ohm's law, again, to find RTH, so we can find the ratio between them. So VAB divided by 1 amp, and that's going to equal simply 14.35 ohms. Yep, so that's our answers. So we've got 14.35 ohms for the resistance, and obviously for our voltage, Thevenin is going to be 0 because we don't have a independent source before, obviously, after we connected, before we connected the current source. So yeah, that's question 10. I'll hand it back over to Otto to complete question 8, and then we'll finish up with the last few questions.
All right. Thank you very much, Luke. Fantastic stuff. All right. So let's condense a bit of this. Just going to select it all. Try and select it all. But little issues. All right. And just shrink it a little. Move it up. Yep. Yep, that works. Right. So, number 8 now. Let's do this. Alright. So, back where we left off. Calculating Thevenin, Thevenin. Thevenin always comes first because it is just the voltage VAB. We have a voltage-dependent current source here. So, once again, we're taking the voltage plus minus VR3, and then we're multiplying that by 4. Okay, and that's what's coming out of here. Now, quite frankly, because we're multiplying by a whole integer to get current, we know it's going to be an inexorbitant amount of current coming out of this dependent current source. Okay, so let's just let's apply. I reckon we do nodal because the current through here is 0 because we got open circuit over here. The 200 does nothing. So in actuality, V3 minus is just VA. So I'm just going to label that as VA. Okay, and I'm going to label this one as VX. All right. Let's take a nodal at Vx. I love my nodal. Let's do this. So we have Vx minus 10 on 1k plus Vx on 1k because it's minus 0 going straight down to ground through R1. And then we have to add on Vx minus Va on 500. All right? And so that's the sum of currents going out equals sum of currents going in, which I'm calling 0 because I'm taking current going out of these 3 directions. Okay, and once again, we're going to group up Vx. Vx, it's 1 on 1k plus 1 on 1k, which actually becomes 1 on 500, and then add 1 on 500, actually just becomes 1 on 250. Equals Va, 1 on 500. And then we chuck this 10 over there to say plus 1 on 100 because it's 10 over 1,000. Fantastic stuff. All right, that's equation 1. Now I need to do equation 2. So we go VA. So this is at Vx, now VA. All right, so VA, we do the exact same thing. Currents going out is going to be VA minus Vx on 500. This 200 does nothing right now, so no current there. And then it equals the current coming in. Current coming in is because of the dependent source. And so we say 4 times Vx minus Va. Alright? And this actually gives a very interesting result because both of these terms are in terms of Vx minus Va. And therefore, the difference has to be 0. You can actually do this very easily because this says, VA 4 plus 1 on 500 equals Vx 4 plus 1 on 500, right? And so Va equals Vx. Or in other words, there is no current going through this 500 ohm resistor. Yeah? Rather riveting stuff. And so we have Vx equals Va equals Thevenin, which is what we're looking for. We sub it back into the first equation. They're equal. You subtract 1 on 500 from Vx, you get 1 on 500 of Vx remaining, right? So you just do Vx 1 on 250 minus 1 on 500. Oops. Equals 1 on 100. This simplifies to just 1 on 500. Oh, the rubber really does not like to work. There we go. Multiplied by 500. Vx equals V Thevenin equals 5. Fantastic stuff. So that's how we do number 8. Now we need to do the R Thevenin, which is where it gets a little bit more interesting. So what I'm going to do is I'm just going to select all my working out, and I'm going to throw it off to the right. Okay? This is just for the sake of me keeping my working, as you should keep yours. And let's continue. All right. So now this contains both independent and dependent. So that means I cannot use type 1, right? Method 1. I have to use method 2 or 3. I'm going to use method 2 because that is far simpler by my opinion. And so method 2 to calculate R Thevenin. Method 2, remember, we need I short circuit. So I'm going to short circuit this and recalculate how much current is coming through here, which is the current going through the 200 ohm resistor. All right. If we do nodal again, why not? The equations for Vx are identical, so we don't need to change those at all. We can just look over here, and we have our equation. Whoops. Give it just a second. Trust in the process. Oh my. It does not like selecting the highlighter. Anyways, this is our equation for Vx from the nodal equation at Vx. We can keep that. And now we just need to recalculate the nodal equation at VA. So VA, we're going to look at, okay, VA minus Vx on 500 plus, now we're going out of here, so that's going to be VA on 200. And this term is our I short circuit. And this is going to be equal to 4 times VA minus Vx. No, it's going to be X minus A. That's correct. Yes. So it's very similar to our first nodal equation in terms of VA, except now we have this fancy term for I short circuit. All right, let's rearrange. We immediately have all the VAs. We can immediately have all the VAs on one side, so we get 4 plus 1 on 500 plus 1 on 200. Let's give it a second to load. Yep. And this much is going to be equal to Vx 4 plus 1 on 500. Now we see this little 1 on 200 term. It wasn't there before in our previous nodal, and it's the key to this entire equation. It's why we actually have an equation now. And so we can actually put Vx in terms of VA here, and then just solve this, which would be really cool. So, I mean, we've got 2 equations. Let's pick one to use. We're trying to find VA, and so we can find VA on 200. So I say we go ahead and chuck this bit using the fancy little trick over here where I just divide without needing to redraw anything, and sub it in. So I say this bit comes over here, this bit comes over here to tell me I have VA and this disgusting equation, which is 4 plus 1 on 500 plus 1 on 200 over 4 plus 1 on 500 times 1 on 250 equals VA 1 on 500 plus 1 on 100. Okay? Now I can divide VA by 200 to give me I short circuit, so I'm actually just going to do that right now. So this just becomes I short circuit times 200, yeah? So I get I short circuit equals this big thing dividing this guy. Actually, sorry, I can't do that just immediately yet. I still have VA over here. Let's simplify that first. Chuck it in over here, minus 1 on 500, and let's see how that goes. So this is a bit of a big equation. So let's think about this. The 1 on 200, I'm going to simplify for the first time in the stream. and this is 0.002, to my knowledge. Yes. So we're going to add them together. So that's VA, 4.007 on 4.002 times 1 on 250 minus 1 on 500 equals 1 on 100. So I'm just going to write that as 0.001. Sorry, 0.01. My bad. Anyways, we have this, and we just divide, okay? And so, I short circuit times 200 is going to be equal to 0.01 over this mess, right? We do get a fair number of messes in electrical circuits, especially Thevenin, but please do not be discouraged. It is meant to look that way most of the time, unless you made a mistake, then it's on you. All right, so that is I short circuit. We just divide by another 200, so I'm just going to rub this out, and then times 200. Fantastic stuff. Left as an exercise to the reader. That's I short circuit. That's not what we want. We want R Thevenin. So we'll just do V open circuit, which is our V Thevenin, and divide it by this value. So we would go 5 over this, so 5 over that would give you V Thevenin. So let's actually just take all this. Wow, it didn't even interact. Good laptop, I swear. Alright, so we say R Thevenin equals V Thevenin on I short circuit equals 5 over, and then paste in what we had there. Alright? And you can track that in your calculator, gives you your number. Alright? Lovely stuff. That is number 8. And wow, that was a banger. So, let's move on. We have question 11. Please excuse the slides loading. So, question 11, we have a dependent source. It is a voltage-dependent voltage source, and we have 2 independent sources, right? And so, let's think about this. To make this a little neater, I will relocate a bit of lathes working, just vertically. So we'll select that all, and we'll just try. Oh, okay, it's not having the funnest time, but let's see what we can do in this time. And double check that it's not running into other working. Oh boy. Move it further to the right, just so we keep that. Alright. And I'll just draw a thing. Good stuff. Alright. Let's move on to question 11. These questions will usually take a fair bit of space to do your working out. Oh wow, it is... There we go. Okay, so V Thevenin first. Let's think about this. We have a 4 volt supply, immediately jumping into A, but then resistors, dependent source, current source. So what are we going to do? I'm going to say ideally we use nodal, because there's one node we need to think of, right? Please do not overcomplicate. One node we need to think of. Why? Because there's no current going through this way. There's no voltage drop over the 50 ohm, and so we just need to add 4 volts to get to A from this node. So I'm going to call this node not VA, VX, okay? So we perform nodal at VX. Very interesting question. We say VX minus this voltage here. What is this voltage? It is going to be 2 times V plus minus V minus, which is Vx. That's crazy, okay? Vx minus 2Vx on 100. We have a 100 ohm resistor there. Mind you, we're assuming everything goes down and out of here. Mind you, there's no current, so we actually don't need that one. Alright, so that's the first one. Add on the next one coming out. It's actually going the other direction. So we say plus minus 2. And then the next amount going out is through this 75 ohm resistor, which is to ground. Okay, so Vx on 75. Fantastic stuff. Alright, and that equals the current going in, which is 0. Group in our Vx's, we end up with minus 1 on 100 plus 1 on 75 equals 2. And bam, you got Vx equals 2 over that number. And so 2 over 1 on 75 minus 1 on 100. Okay? Good stuff. But that's not Thevenin just yet. That is not Thevenin just yet. Thevenin is, as we mentioned before, going to be 4 volts higher, right? There's a 4 volt jump over here. And so it's 4 plus 2 on 1 on 75 plus, sorry, not plus, minus. Let's rectify that. All right. Lovely stuff. That's Thevenin. Now, our Thevenin, dependent and independent, we need to find I short circuit. So we're going to pull it together. Now, let's grab our working over here. Ooh. Give it a sec. Bam. Drag it upwards so we can all see. Alright. Now we're going to calculate. Ooh. Oh my. Alright. Our Thevenin time. Let's do this. So, method 2. We need to find I short circuit. And to do so, I am actually just going to do nodal again, because it's the same node, except we do have a current going through here. Okay? So we pretty much just run back the exact same equation, Vx minus 2Vx over 100 plus minus 2 plus Vx on 75 plus, now we have our last one, which is going to be running this way. We connect this to ground, so this point right here becomes minus 4 volts, okay? Because it's the negative end of a 4 volt supply, okay? There will be a 4 volt gain to A, VA, but since we've short circuited, VA is now 0. So we say Vx minus 4 on 50, okay? And this is going to equal to 0. Now, mind you, it is this current, which is I short circuit. Wrong way around, my bad. This one is I short circuit. This is the value we want to find. And so, let's do it. So, what I'm going to do first is group my Vx's. I end up with minus 1 on 100 plus 1 on 75 plus 1 on 50. Chuck everything over to the other side. What do I get? I end up with 2 minus 4 on 50. Yeah? Alright. Minus 4 on 50. 4 on 50 is going to look like, what, 0.8? No, 0.08. Okay? So we can say 0.08, and then we get 1.92. Okay? That's what we get there. We're happy. Okay? Vx equals 1. That's a horrid 992 over, in brackets, 1 on, actually this 1 on 50 minus the 1 on 100 can actually just turn into a 1 on 100. So we can say 1 on 100 plus 1 on 75 Okay, fantastic stuff. We got Vx. Now we have to find I short circuit. And so we go and chuck that in the equation. So we can say R Thevenin equals V Thevenin over I short circuit, which is going to be equal to 4 plus 2 on 1 on 75. I've got to stop writing the plus. 1 on 100, all divided by I short circuit, which will be 1.92 over 1 on 100 plus 1 on 75, plus 4 on 50. Right, bam. To be plugged into your calculator. You may do that at your own leisure. Nice. Let's move on to, we have 4 questions remaining, I believe. Yes. 12 through to 15. And I think we'll go through this one first. They're a bit miscellaneous. So right here, we can see all independent sources. Lovely stuff. And so, all independent sources calls for method 1, right? Let's do this. So, V Thevenin, we go ahead, calculate this voltage. How are we going to do that? Well, we know all the current through here is going through there, so it's a little bit apparent. We know that 2.5 amps are running through a 3 kilo ohm resistor, and so the product is just the voltage. How crazy is that? All right, so you get 3K times 2.5 because V Thevenin. All right, now for R Thevenin, mind you, this is method 1. We turned them off, and this, when we turn it off, just becomes an open circuit. How strange. Mind you, we did have a little bit of a troll 0 volt independent source, this one, which was just always short-circuited. But when you redraw this circuit, it actually just turns into source, resistor, and then a source resistor, right? And so we really know almost everything we need to know about this circuit already. And since turning off this independent source will make an open circuit, what the terminal sees is just what's running through here, which is just the 3K. All right, let's speed through this. Number 13. We have V Thevenin. We see a dependent source over here, which has 3 times the voltage over R20. And let's think about the method we're going to use to solve this. We could use 2 meshes, or we could use 3 nodes. Or 3 or so nodes, that is. I'm going to go with the method to use 2 meshes. Okay? Now the crazy thing with this method is I already know what this mesh current is over here. And that is just going to be what's running through this independent current source, which is 0.4 amps. And so I just say I1 equals 0.4 amps. And then I'm going to look at mesh 2. So mesh 2. This is this one. So let's run it in from ground. We go from the negative side, minus V plus, minus V minus. Let's think of this. What is this going to be? It is just 0.4 amps times 20 ohms. Okay? So minus 0.4 times 20 times by the gain 3. This is where 3 comes from. Okay? So this right here is the voltage over that source. We continue. We go through this resistor, plus 35 times I2. we go through this 25 ohm resistor, and it gives us a funny equation because the current going through here is going through the difference of the two meshes, right? So we say plus 25. Remember, I'm talking about it as though it has a plus and a minus here. That's how it's running through the circuit. And so I say I2 minus 0.4. This is the difference between the two sources, okay? This is how I get the voltage over this resistor. I continue. It is only part of one mesh, this 20 ohm resistor, so I say plus 20 I2, and then a 0 volt supply, which contributes nothing. This will sum to 0. Good stuff. All right, let's simplify. We chuck these full numbers over to the right-hand side, same with this one, and we group up everything in terms of I2. So I2 with a 35, a 25, and a 20 is going to equal to 5 times 3. Mind you, this is what I simplified it into, plus 0.4 times 25, which is 10. All right, so this much equals 25. I2 equals to 25 over, what's this number, 80? All right, that's I2. Now, why was finding I2 important? Let's think about this. I want the voltage running down from here. I'm able to find the voltage over this guy. I'm able to find the voltage over this guy. I can only find the voltage over the R3 value if I have this mesh. And so I say Thevenin equals 20 times 0.4 plus 20 times I2, which was 25 on 80, which gives me a total of 5 plus 25 on 4, which we can simplify to 11 and a quarter. All right, that's Thevenin. Good stuff. Now we need to find R Thevenin. We have a dependent source and independent sources. Method 2 is typically the way. It is a very similar problem. However, now we have a third mesh. Isn't that interesting? Now, the funny thing with this mesh is there is absolutely nothing driving it. There's absolutely nothing driving it. And what I mean by that is there's no voltage source. I can have currents, but those currents are typically going to be net from the other sides. So what am I going to do? Well, I just make another mesh equation, I3, okay? Now, this does mean a few things. I do already know what I1 is. Let's label that correctly this time. The mesh equation for I2 does change, and the mesh equation for I3 is introduced, right? So I reckon we do this. So R Thevenin. First, reanalyze your mesh 2. Mesh 2, once again, we have minus 0.4 times, actually, it's not so simple, because the current going through this resistor, the 20 ohm resistor which we're referencing for this dependent source, is now subject to I3 as well. And so, it is equal to I4 minus I3 times 20 times 3, okay? So that's what's coming out of this dependent source. We say plus 35 I2 plus 25 I2 minus 0.4, and then we also say plus 20 I2 minus I3 equals 0. Right? The 0 volt source still contributes nothing. Big long mesh equation, which simplifies down into, let's think of this, group I2s. We got 35 plus 25 plus, 35 plus 25 plus 20, which is just going to give me 80 as per before. And I throw everything else onto the other side. Throwing everything else onto the other side is going to give me 10 from this one, plus the I3 in here. Now, using the I3 in there, first of all, I get a 15 from the 0.4, but I get a minus I3 times 60. Alright? And that is a little goofy. Alright. I may have made an error previously. Yeah, so the error previously was this number is actually 8. So let's fix that. 8, 24, 34 over here. So we get an 8 over here. Yeah. Alright, yes, that was a small error on my part. My apologies. Alright. There we go. That's more like it. So, we don't get a 60 here. Yeah, we do get a 60 here. But we get a 24 over here. Alright. So now we have our first equation. Now we need to do our second equation using the mesh about I3. Doing this mesh, we go again, and it's actually two of the elements we've already considered. So I go through here, I say, okay, I have a 20 ohm resistor, I'm looking at it through this way, and so I say 20 times I3 minus I2, okay, because that's the difference in current I'm seeing from this direction. And I go plus 20 times, this is for the top resistor now, and once again, the difference I see when going in this direction is this, because I know I1 is equal to 0.4. Total to 0, okay? Mesh voltage is 0. So, we do this, we get another equation in terms of I2 and I3. And so, grouping I3, we get 40 I3 is going to be equal to 20 I2 plus 8. Alright? Now I have our two equations. I'm just going to simplify this to 34 minus I3 times 60. And let's simplify, right? What do I need to find I short circuit? I need I3. So, since I need I3, I'm going to substitute I2 for I3s. So I go over here, which is over here, I2. I'm going to substitute in 34 minus 60 I3 on 80, which is taken from this here equation, okay? Plus 8. Group everything together. 20 on 80 is just 1 on 4, so I send over 15 I3 to the other side, so I get 55 I3. Mind you, this is just redistributing terms. 55 I3 equals 34 on 4 plus 8. Bam. And this right here is our I short circuit. Okay? This is our I short circuit. That is what I3 is. And we're going to perform a division. So, R Thevenin equals V Thevenin over I short circuit, which is going to be equal to 8 plus 34 on 80 divided by 34 on 4 plus 8 divided by 55. And bam! That's method 2. How are we feeling about this? Alright. So that's 12 and 13. We've got 2 more questions to go, and technically 15 more minutes in the room. I think we do have the next hour free, so more than happy to get all of them bashed out. Alright, so number 14, we're going to calculate Thevenin. Let's think about this. VAB, oh my, they are all independent sources, alright? But the circuit is a little bit convoluted. How are we going to get here? How are we going to get here? That's the question. So, I propose we use 2 meshes. Now, why do I say that? Because I see 2 meshes, I see 3, 4 3, 2 or 3 nodes. No, 3 or 4 nodes, right? That I would need to consider for my equations. So, I'm just going to use the 2 meshes, right? I'm going to use I1, I'm going to use I2. But what's the funny thing here? I already know the mesh currents. How crazy is that? I got my I2 is equal to 9 and I1 is equal to 7. So I already know these. I know I1 is equal to 9 and I know I2 is equal to minus 7. Wow, that's made things a lot easier. Now, how do I get from B to A and measure voltages? I need to track it around somehow. The way that I'm going to go is along this here resistor path. Okay, so I'm going to run up this resistor, across this resistor, and across this resistor to get there. Okay, now, why am I choosing this route? I'm able to calculate voltages over resistors very easily. I cannot do so for current sources, right? And so, plus minus, plus minus, plus minus. And that gives us Thevenin equals VA from B, which is equal to, wait a minute, I've done this the wrong way around. Pluses and minuses should be backwards. My bad. So rather, I'm measuring the voltage from the top to bottom, okay? So I start with the 17. What's the current going through it? It's just I1. So I1 is 9, so I have a 9 over there. Now I look at the 23 ohm resistor. What current's going through it? From this direction, it's I1 minus I2, right? And so I write 23 I1 minus I2 is that. And then next up, I have my 33 ohm resistor, and just I2 is running through it. Rather, minus I2 is running through it. So I have just so. Now that's a big voltage. That is a big voltage. It's a big happy voltage. Now it's a very easy way that we get to do this. Some of these questions, it's about being a bit inventive, even though the circuit may not be exactly conventional, right? Fantastic stuff. So that's Thevenin. And I guess the big takeaway from this question is don't be afraid to attempt to simplify it, okay? You know the currents, you got this, you got the tools. Now we're going to do Thevenin. Just remember, this is method 1. I keep on forgetting to bookmark these with tags for section 2, like method 2 and such. But anyways, let's keep on going. Thevenin, method 1, we turn them off. So that's cut off. And now I have this kind of dangling resistor over here. I'm actually just going to rub out everything I've drawn, just so everyone can see it a lot clearer. Because method 1, we only care about the resistors and what happens to the sources. So let's do that. This source gets cut out, this source gets cut out. They are current sources, they turn off to be an open circuit. Now I have this dangling resistor to nowhere, so I can kind of also cut that out since no current goes through it. Anyways, it doesn't contribute to anything. Yeah? Nice. So now I just, once again, have these 3 resistors lined up perfectly in series. And so I say Thevenin equals 17 plus 23 plus 33 ohms. Fantastic stuff. One last question, 10 minutes, we've killed it today. Hope you guys are killing it outside of the room or in the future. Who knows? Number 15. Thevenin comes first. And this is a slightly different question to much earlier, okay? To see if we've pushed through. Actually, wait, is it the exact same question as earlier? That might be my mistake. It's a very similar question. It's a number 5. But let's see how it goes. Thevenin, can we use a different method for it this time? Previously, I used meshes. How about we try using nodes? Right? Let's try nodal for this one. Nodal. Oops. With a big exclamation marks. Okay. So, what nodes do we have? We have VA and we have VX. Technically, we do have a node here, but I don't like considering it. Why don't I like consider it? Because I already know the voltage there, right? Why would I put a node there if I already know the value? The node is there to indicate something I don't know. That's why I label these ones. Yeah? VA and VX. They're things I don't know, things I can find out. And so, I will not be labeling the node above the 20 volt resistor if I were to label it at all. Wow, it is really not interacting. That's interesting. Anyways, I'll just label it 20 volts, right? Wow, I think we're... Attendance form, make sure you do it at some point. Oh wow, my OneNote actually crashed, so it closed. That's interesting. Let's get it back up. Give it a second, but back we are. Okay. Yeah, I think writing the 20 there actually made it kind of lose its screen. Anyways, so that would just be 20 volts. No need to assign a nodal, what is the current going in and out? You use the currents to put an equation in terms of voltage. Yeah? Alright, so let's do nodal. VX node, what currents have we got? We've got currents going out, going out, going out, going out. Alright? I like labeling everything going out or going in. I like going out, okay? Going out is nice because I know the VX symbol is going to be positively signed, and so there's nothing to really worry about. So VX on 20, that's the R1 value. Now the R4 value, we do VX minus 20, so that's going to the 20 volts. Did I say VX minus 20 before? VX minus 0 because that one's going to ground, just to make sure I'm not falsifying anything. That's a 10 ohm resistor it's going through. Next up, VX minus VA, that gets divided by the 50 ohm resistor because that's going through the 50 ohm, and we have a 1 volt going out. So we put a plus 1 over here. This equals 0. So now I can redistribute everything, put X purely on this side. So I say Vx multiplied by 1 on 20 plus 1 on 10 plus 1 on 50. So that's just crossing out this one, crossing out that one, crossing out that one. Is going to be equal to, throw everything else on the other side. I have a 20 on 10, which is just 2. I have a minus 1, and I have a plus VA on 50. Fantastic stuff. So that's first node. Second node, VA. Let's think about this. VA, I just have consideration of these two, right? In fact, this is just 1 amp going in, so I can say the nodal equation is at VA. Reminder, nothing goes through here, and so there's nothing going into the node, into the terminal, because it's classified as an open circuit. We say VA minus VX on 50 is equal to 1. VA is equal to Vx plus 50. Good stuff. Does that help me? Will it help me? It should, because now I can plug back in, okay? We have 2 equations in terms of 2 variables. We should be able to solve it. Just plug one into the other. So I want to find VA, so I'll turn Vx's into VA. So this bit, I chuck on the denominator over there, and I have some fun. So VA is going to be equal to 1 plus VA on 50, all divided by 1 on 20 plus 1 on 10 plus 1 on 50, which looks a bit like an equivalent resistance. That might or may not be a spoiler. Plus 50. Alright? So VA is Thevenin. Let's calculate this. We still have a VA over here, so we need to throw that onto the correct side, collect like terms and such. It's these little bits where we need to throw things again when we have complicated denominators, it's what really complicates these calculations, but do not worry too much. So we end up with VA, sorry, I should not do an equal sign immediately, group the VAs, so I get 1 plus, it'll actually be minus, my bad. So 1 minus 1 on 50, all divided by 1 on 20 plus 1 on 10 plus 1 on 50. Now, yes, this is going to be a bit disgusting. In fact, I would urge you simplify it earlier. It's alright if you're 0.002 off of it, as long as the question's in the realm of ones. Equals 1 over, actually this is just 20, sorry. This actually just turns into 20 parallel 10 parallel 50. So I'm just going to write it as that to save some space, plus 50. And so I say, I can actually do the same over here, just to simplify the expression of it. Just say 50 parallel 10 parallel 20, all divided by 50. So VA equals Thevenin equals, we chuck this on the denominator, 20 parallel 10 parallel 50 plus 50, all divided by 1 minus 50 parallel 10 parallel 20 over 50. Good stuff. Now our Thevenin. Nearly finished. Done fantastically today. I hope you guys have a fantastic time as well, and then we'll make a few announcements. So, our Thevenin, what do we get? Let's erase all the little scribbles I made on here and think about what we do. So, method 1, once again, turn off our sources. The current source, open circuits, the voltage source, short circuits, and once again, I look through, I get my 50 ohm. What am I adding to it in series? The parallel of 10 and 20, right? So 10 parallel 20. That was an atrocious 20. All right, there we go. Good stuff. All right. Fantastic job, everyone. That is the solutions to the Thevenin B questions posted on our Discord and resources on the drive. And now to just plug some future events. Next week on Friday, we will be holding a ELEC Quad 1 midterm crash course. And yeah, that should be fantastic for you guys. I believe your midterm exam will be on week 5 Thursday. Yeah, in your lecture time. But please do check with your lecturer and your stuff. Remember, ELSOC, we're here to help you, although we may not be 100% on your timetable, okay? Take it with a grain of salt. Do your best. This is the solutions to the Thevenin B. And yeah, enjoy.